So to most, this type of testing is nowadays best known as fuzzing. But again, if you come from quality assurance background, you are probably more familiar with negative testing or robustness testing, grammar or syntax testing. Those approaches have the same purpose, so trying to explore the infinite amount of tests that and infinite input space in order to find those crash level issues or memory leaks or busy loops from the system. In our talks, we don't really touch on the base of on the area of random mutation fuzzing because that's not really a smart way of doing it. Instead, we focus on more optimized smart means of fuzzing, meaning template-based and specification-based, model-based fuzzers. And very quickly summarizing those again for those of you who have not attended our seminars before. Template-based fuzzing basically means that you take a traffic capture or seed files or whatever you want to fuzz, and then you build your models from those templates, and then exercise all the test generation techniques to those. Whereas specification-based fuzzing requires a lot of work in building the model from the specifications themselves, and then the same test generation tools and techniques are used to generate those test cases. So the biggest difference between these is that template-based fuzzers are, of course, always very general purpose. You can use exactly the same tool to test hundreds of different protocols. Specification-based fuzzers are much more targeted, get much better test coverage on that specific protocol that they are targeting on, but cannot that easily be used to test other protocols except the one that they are focused on. So coverage is actually the most important aspect of fuzzing. So I have divided coverage in two different categories. The precision is about the protocol awareness, and accuracy is about the security awareness. So what areas of protocols you test and what type of anomalies you actually use in those tests. And combination of this then is a measurable thing that you can use to compare tools and also estimate how well something actually was tested. In our tools, you can, of course, also change how good coverage you want to do, because challenge in all negative testing is that you can always create more test cases. It's very easy to create more and more fast test cases, but the intelligence of those test cases becomes less, the effectivity becomes less because the more semi-random or non-optimized tests and anomalies you add, the less value they actually provide to the test execution. So if you only have like an hour for testing, you optimize the anomalies. If you have weeks and weeks of time, you create more test cases, adding slightly more coverage, but of course increasing the execution time. I'm not going to go through the traffic capture fuzzing area in the example, so I thought I'll just show them very quickly for those who are not familiar with it. So in the top left corner, you see our network analyzer product, which is used to monitor traffic, in this example just from one location, but you can of course have a wide set of different tabs or recorders in place. And then you can look at all the communications happening inside and outside the device, and then export those into PCAPs, which is a very common format used for network traffic, like Wireshark and such. Loading that PCAP into the traffic capture fuzzer creates a protocol model that you can edit and modify, and then basically generate test cases from. So the process from the capture, model building, and then execution is just 5 minutes of time, and you can get pretty good coverage, although nothing close to what specification-based fuzzers can do. But it's a very quick way of doing fuzzing. And from performance perspective, traffic capture fuzzers are often slightly faster than specification-based fuzzers because the complexity of the model can be less extensive. So often, like in our study, we noticed that the speed can be really like hugely, significantly better than with specification-based fuzzers. Again, that's a compromise between coverage and speed, but you might be interested in seeing that if you actually want to generate high load, then traffic capture fuzzers can actually be one of the areas that you might want to look at. But then test execution is exactly similar. Those of you who have used our tools, traffic capture fuzzer looks, or every model created by the traffic capture fuzzers looks like an individual test suite for individual protocol, and you will browse them. You can browse the results, and you can see documentation for every single test case from the tool itself. So, if I recall correctly, this is the last slide of the introduction overview part. I will end this with, to me, what I see like the key questions every time you consider and look for fuzzing tools and techniques, the key questions to test coverage, and those are targeting those two areas I also explained. So the protocol coverage, what areas you test, and how those protocols are modeled, and where those models actually are built from, and then how well something is tested, which actually means how those anomalies are actually integrated into the test generation process, and how everything is documented, and how you can actually measure what actually was tested and how well everything was tested. So, of course, if you have tens and tens of different protocols you need to test, for example, if you are testing security devices or antivirus products, then you might not have time or resources to do specification-based testing for everything. Then you can do compromises between the coverage and speed and price and so on. But the key topic for today is really on fuzzing performance. And